So this trend is called ionization energy. Ionization energy is the energy needed to remove an electron from a gaseous atom. Energy needed to remove an electron from a gaseous atom. Therefore, it's like an enthalpy. It's a delta H, and it's measured in kilojoules per mole. So it's an actual quantity of how much energy to take away an electron from something to ionize a particular atom. These have equations to them. So here is the ionization energy equation for sodium losing one electron. This would be called the first ionization energy. There are multiple ionization energies for just about every atom on the periodic table for as many electrons as they have. This would be an equation for the second ionization energy of sodium. Notice it starts with having one less electron because it's Na+, and then it loses a second electron and becomes Na plus 2. So this would be called I2, or the ionization energy number 2. You could have a third ionization energy for sodium, so that would be Na plus 2, and it would become Na plus 3, and it would lose another electron, etc. You could have a fourth ionization or fifth ionization energy. All right? It's the energy needed to remove 2, 3, or 4 electrons as you go I1, I2, I3, I4. All right? Stability plays a big role in how much energy it takes to remove these electrons. Stability does. And the general rule is that as you get to be a larger atom, it's easier to remove your electron because you're further away from the nucleus. Conversely, as you're a smaller atom, it's more difficult to remove them because you're closer to the nucleus and closer to holding on to it as well. Stability also makes a big difference in terms of being close to a noble gas configuration. Here, let's take a look at some successive values of ionization energies. We can see here that magnesium's first ionization energy is 738. Its second is 1451, and then you see it takes an astronomical jump to 7,700. Now, if you look at aluminum, its first, second, third are reasonable numbers, and then it takes a big, huge astronomical jump as well. And so this goes on to the stability of these. Let's just take a look at these elements on the periodic table. Here's sodium. If it loses an electron, it now has a configuration like a noble gas, a very stable configuration. That's why the second ionization energy is so high. Magnesium loses one electron and then looks like sodium. If it loses a second electron, now it looks like neon. That would be the I2. Now the third ionization energy we said was astronomically large. That's because it would already have a noble gas configuration and it would be very stable. Aluminum, 1, 2, 3, the fourth ionization energy. So here's aluminum. Loses 1, looks like magnesium. Loses 2, looks like sodium. Loses 3 electron. Now it hits this noble gas configuration. And you can see from this chart that just look at the period 3 elements, that as you hit a noble gas configuration right here, then all of a sudden the ionization energies become very, very big. All right, let's take a look at a couple more example pieces. Here's the electron configuration for neon. Neon has a noble gas configuration of 1s2, 1s2, 2s2, 2p6. I'll put the 1s2 in there as well. And so the outer valence shell electrons would be 8, or the octet rule. Therefore, the ionization energy for it to take away one electron would be very, very large because it's very stable. This would be the equation if you could do that. And so the trend is, as you lose more electrons, the ionization energies increase. And you can see that from here as in aluminum. 578, 1800, 2700. So as you lost more electrons, it takes more energy to take those electrons away. Trend part number 2, elements that are closer to an octet cost more energy to remove an electron. And this, once again, shows that as well, that once you reach that octet, well, it takes a lot of a lot of energy to remove one, a lot of energy to remove one, a lot of energy to remove one, because you are close to a full outer shell like the noble gases are. Here's a trick when they ask you questions about this. Watch your electron configuration. Write out your electron configuration. See how close you are to stable. The more stable you are, the closer you are to an electron configuration of a noble gas, the more energy it will take to remove that electron, the higher the ionization energy. Right? Let's go to the next page and let's look at the general trend for first ionization energies on the periodic table. So the general trend for ionization energies is that they increase up and to the right. And you can see it on this diagram right here, that this is the smallest ionization energy right down here, poor cesium. Its electrons just kind of hanging out there for anybody to grab, all the way up here to helium, whose first ionization energy would be astronomically high because obviously the electrons are really close to the nucleus. It only has 2 electrons, and it's very difficult to remove them. So the general trend is up and to the right. Ionization energy, first ionization energy, increases. So the more electrons and the more protons, the more effective nuclear charge you have, and the more electrons, that's going to the right. So as we go to the right, that's what this arrow means. As we go from left to right across the periodic table, we have more electrons and more protons, therefore more effective nuclear charge, and so that's what holds it tighter. That's why this trend increases to the right. And as you go down a group or a family, you have more electrons, more protons, but the electrons are further away from the nucleus, and so there's less attraction for those electrons. That's why there is a lower ionization energy down here. So here's a couple of rules to go by. So the S and P block elements show a larger range of ionization energies than do the transition metal elements. Generally, the ionization energies of the transition metals increase slowly from left to right across the period, and the F block metals, which are not shown in the diagram, also show only a small variation. And so you can see that here, this D block right here doesn't show a lot of difference because their D orbital electrons are not the ones that usually participate in bonding like the S and P electrons usually do. So in general, smaller atoms have a larger ionization energy. And you can see that these guys all up here have a larger ionization energy than these down here because the electrons are closer to the nucleus. We'll come back in the next video and we'll look at some example problems and some questions that might eliminate a little more confusion on ionization energies.